Hello, my name is Emma Warren, and today I'll be presenting my lab on the topic of charged tapes. The purpose of this lab was to understand the transfer of electrons between the two pieces of tape and calculate how many electrons were transferred. To get a better understanding of this concept, I created my model using multiple pieces of tape, quickly removing top pieces from a base layer to transfer electrons, and finally testing the attraction and repulsion of the tape from different objects. Ultimately, I calculated the electrons left on the piece of tape from my findings. There are several equations and concepts that are essential to understanding this lab. Newton's second law helps with us understand what is happening when there is a change, or lack thereof, of momentum. The force of gravity is used to calculate total net force on the piece of tape, and Coulomb's law, an equation for measuring the force between two charged particles, is used to determine the important question of the quantity of electrons transferred. Before any formal calculations, we can learn a lot from just observing the behavior of our newly charged tape. When placed near a human hand or a neutral marker, it attracts. However, if it's placed near another similar U-tape, it repels. To figure out the true charge of the tape, I negatively charged a marker by rubbing it in my hair to collect a negative charge, and when placed near the tape, it attracted. Therefore, the charge of the tape is positive as opposite charges attract. We can also learn from depicting our system in a free body diagram. As the momentum is not changing, we know the net force must be zero due to Newton's second law. This means whatever forces are acting on the tape must cancel each other out. Therefore, the gravitational force must cancel out the force caused by the attraction. This understanding will be helpful in our numerical calculations. Now let's discuss some numerical data that will be helpful when calculating amount of electrons left on the piece of tape. This includes the length as shown in meters, the width, the calculated magnitude of the gravitational force in newtons, as well as the equal magnitude of the electric force as we explained in the free body diagram. Lastly, the repulsion distance between the two pieces of tape, also shown in meters. Now let's get into the findings of this experiment. By reevaluating Coulomb's law to instead solve for Q, we are able to estimate the charge left on tape B to be 9.856 times 10 to the negative 9 with units coulombs. Next, we estimated the number of atoms on the sticky surface by dividing the surface area of the tape by the area of an atom. We found that 3.4 times 10 to the negative 7 atoms were left on the surface. Next, I calculated the number of deficient electrons to be 6.15 times 10 to the 10th electrons, which I finally used to calculate the ratio of electrons transferred, which ultimately resulted in a ratio of 1 electron for every 1.08 times 10 to the 3 atoms. It wouldn't be a physics lab if we didn't have a glow script estimation to compare our findings to. Let's discuss what I did in my code before we get into the questions and answers about the model. First, I used my code from Lab 0 for calculating an electric field produced by a point charge. Then I used it to estimate the charge I would need for the tape to float above, and I found it to be 1.1 times 10 to the negative 8 coulombs. From there, I changed course and represented the tape instead as a string of point charges, with the charge of the tape evenly distributed. Through the concept of superposition, I was able to find a new estimation in a diagram of the simulation and found that a charge of 2.5 times 10 to the negative 8 coulombs was needed for the tape to float. Now let's discuss the questions regarding the simulation. Number 1. The magnitude of the charge on one piece of tape when each piece was treated as a point charge was 1.10057 times 10 to the negative 8 coulombs. The magnitude of the charge of one piece of tape when each piece was treated as a line of charges was 1.432 times 10 to the negative 3 coulombs. And finally, assumptions that I made in both simulations. Number 1 was the strip of tape was equal to 1 point charge, and then in the second simulation, I assumed that the charge was evenly distributed. Now for the discussion. What if the signs for electrons and protons were switched? Would anything be different? If electrons and proton signs were switched, there would be no dramatic change. The forces would remain unchanged, and the only true difference would be the logging of the charge's signs. This is because through the force, charges are multiplied. Even if each charge switched signs, the sign of your final answer would remain the same. And finally, like most experiments, the real-world data does not exactly match that of the model. Why is that? Like most experiments, there is a variation between computational and real-world data. This can be due to a multitude of reasons, but most of which boil down to the difficulty in precise real-world testing. Touching the tape in any way may have transferred more electrons than intended, mass or length calculation could be flawed, and a multitude of other errors could have happened during real-world testing. In conclusion, this lab bettered my understanding of electric forces and how they interact with environments around them by transferring electrons between pieces of tape. Thank you for listening to my presentation. I hope you were able to learn a little something along the way about electric fields, charges, and more.